Welcome back to the channel. Now, have you ever been driving down a beautiful, smooth road and wondered, wow, how did they make this so perfect? And then, just a few miles later, you're on a road that looks like it's been through a war zone, with potholes big enough to swallow a small car, even though it was just paved last year. What's the secret? Why do some roads last for decades while others crumble after a single rainy season? The answer, my friends, is all about the sticky black stuff that holds it all together. Bitumen. And more importantly, how we test it. I'm engineer Hamza, otherwise known as the Meticulous Engineer, and in this video, we're diving deep into a super popular topic from Civil Engineering 801, bituminous materials. This isn't just theory, this is the science behind building roads that last. We're going to break down every single test that engineers like me use to figure out if a batch of bitumen is good enough for our roads. I'll explain it all step by step, in a way that's super clear and will get you ready for any exam. We're talking about turning that complex textbook chapter into something you can actually understand and use. So, whether you're a civil engineering student cramming for finals, a postgraduate researcher digging into pavement materials, or a site engineer who has to make critical decisions every day, this video is for you. What we're covering today is absolutely crucial, not just for passing your exams, but for building the infrastructure that we all rely on in the real world. So grab your notebook, get ready to ask questions, and let's engineer some seriously durable roads together. Okay, first up, we have what is probably the most fundamental test of them all, the penetration test. So, what's the big idea here? Imagine you're trying to build something out of clay. You wouldn't use clay that's rock hard, and you wouldn't use clay that's basically soup. You need it to be just right. It's the same with bitumen. The penetration test is our way of measuring the hardness or consistency of the bitumen. It tells us if we're dealing with a tough, sturdy binder or a soft, goopy one. This single number is the first clue in deciding if this bitumen is right for the job, especially when we think about the climate it will have to endure. So how do we actually do it? It's a pretty clever and standardized setup. We take a small sample of our bitumen and we put it in a container, making sure it's at a very specific temperature, usually 25 degrees Celsius, which is like a standard room temperature. Then we bring in the star of the show, a standard needle. This isn't just any needle, its size and weight are precisely defined. We position this needle just so it's touching the surface of the bitumen, and then, for exactly 5 seconds, we let a standard weight of 100 grams push the needle down into the sample. It's like a tiny, controlled poke. After those 5 seconds are up, we measure how far the needle penetrated into the bitumen. We measure this distance in units of 1/10 of a millimeter. So, if the needle sinks down 8 millimeters, we say the penetration value is 80. A higher penetration value, like 100, means the bitumen is softer because the needle sank deeper. A lower value, say 40, means the bitumen is much harder. It's a simple, inverse relationship. More penetration equals softer bitumen. This test is so foundational that bitumen is often graded and sold based on its penetration value, like 60-70 pen grade. Now, why does this matter so much? Think about where you're building the road. If you're in a really hot climate, like in many parts of Africa or the Middle East, you don't want a soft bitumen with a high penetration value. The sun would heat it up, it would become even softer, and the road would start to deform and rut under the weight of traffic. For hot climates, you need a harder bitumen with a low penetration value. Conversely, in a very cold region, a hard bitumen would become brittle and crack. There, you'd need a softer grade to maintain flexibility. So, the penetration test is our first critical decision point. It's the gatekeeper that helps us match the bitumen to the environment. It's not about good or bad bitumen in an absolute sense, but about finding the right bitumen for a specific location and its expected temperature range. Getting this wrong is a recipe for premature road failure, and that's why this simple, elegant test is step number 1 in ensuring a pavement's longevity. It's our first line of defense against building a road that melts in the summer or shatters in the winter. Alright, we know how hard the bitumen is at room temperature thanks to the penetration test. But what happens when the sun comes out and the pavement starts to heat up? That's where our second crucial test comes in, the softening point test. The name pretty much says it all. We're trying to find the exact temperature at which the bitumen loses its solid-like properties and starts to behave more like a liquid. It's not a true melting point, because bitumen is a complex mix, but it's a critical indicator of how it will perform in hot weather. A higher softening point is a very, very good thing for roads in warm climates. The apparatus for this test is really cool, and it's called the ring and ball apparatus. Here's the setup. We take 2 brass rings and fill them with our bitumen sample. Then we suspend these rings in a beaker of water. Next, we place a small standard-sized steel ball on the center of each bitumen-filled ring. Now, the experiment begins. We start heating the water in the beaker at a very controlled, steady rate, usually 5 degrees Celsius per minute. We're watching those steel balls very, very closely. As the water heats up, the bitumen in the rings gets softer and softer. Eventually, it gets so soft that the weight of the steel ball starts to push it downwards, stretching the bitumen into a little drooping loop. We keep watching, and the moment that drooping bitumen, carrying the ball with it, touches a metal plate placed exactly 1 inch below the rings, we record the temperature of the water. That temperature is our softening point. We usually do it with 2 samples at once and take the average for accuracy. It's a simple, visual, and effective way to define that transition from solid to soft. So what's the big deal with this number? The softening point tells us about the bitumen's temperature susceptibility. A bitumen with a high softening point, say 55 degrees Celsius, can withstand much higher pavement temperatures before it starts to get dangerously soft. This is exactly what you want for a road in a hot city that sees a lot of heavy, slow-moving traffic, which generates even more heat. If you used a bitumen with a low softening point, say 40 degrees Celsius, that road would be at high risk of rutting and shoving, creating those ugly and dangerous grooves you see on failed asphalt surfaces. In essence, the softening point is our primary defense against heat-related deformation. While the penetration test gives us a baseline consistency, the softening point test predicts how that consistency will change as the temperature climbs. For engineers, this isn't just an abstract number. It's a direct measure of the road's ability to resist bleeding, where the bitumen oozes to the surface, and rutting. Selecting a bitumen with an appropriate softening point for the local climate is non-negotiable if you want the road to survive its first summer, let alone last for 20 years. Okay, we've tested for hardness and resistance to heat, but there's another property that's just as important: flexibility. A road pavement isn't a completely rigid slab. It needs to have a little bit of give. It has to flex under the weight of thousands of cars and trucks every day, and it has to expand and contract with temperature changes without cracking. This is where the ductility test comes in. This test measures the ability of bitumen to be stretched into a thin thread before it finally snaps. It's a direct measure of its adhesive and elastic properties, which are key to holding the aggregate particles together. The procedure for the ductility test is as elegant as it is visual. We start by molding a sample of bitumen into a standard briquette shape. It kind of looks like a little dog bone or an hourglass. This specific shape ensures that when we pull it, the stretching happens in the narrow center portion. This briquette is then placed in a machine called a ductility testing machine, which is essentially a long water bath kept at a standard temperature, typically 25 degrees Celsius. One end of the briquette is held fixed, while the other end is pulled away at a slow, constant speed, usually 5 centimeters per minute. We just watch as this bitumen sample gets stretched longer and longer and longer, forming an incredibly thin thread. It's actually pretty amazing to see just how far it can go. The test ends the moment this thread breaks. We then measure the total distance, in centimeters, that the sample stretched before it snapped. That distance is the ductility value of the bitumen, so if it stretched out to 75 centimeters before breaking, its ductility is 75 centimeters. A higher number means the bitumen is more ductile, and therefore a better binder. But why is a stretchy bitumen so important for a road? Think of the bitumen as the glue that holds all the stones, the aggregate, in the asphalt mix together. If this glue is brittle with low ductility, any movement in the pavement, whether from a heavy truck passing over or from the pavement cooling down rapidly at night, will cause it to crack. These small cracks can then grow, let water in, and ultimately lead to the complete failure of the road. A ductile bitumen, on the other hand, can stretch and deform without breaking, maintaining a continuous waterproof film around the aggregates. This property is especially critical in colder climates, where the risk of thermal cracking is very high. A bitumen might have a good penetration and softening point, but if it lacks ductility, it will fail when temperatures drop. Therefore, the ductility test ensures we have a binder that is not only strong, but also tenacious and flexible. It guarantees that our pavement can bend without breaking, providing the resilience needed to withstand the relentless stresses of traffic and temperature for years and years. It's the test that ensures our road has the toughness to go the distance. So far, we've talked about hardness, softening, and stretchiness. Now we need to talk about flow. Viscosity is simply a measure of a fluid's resistance to flow. Think of the difference between pouring water and pouring honey. Honey is much more viscous than water. For bitumen, viscosity is everything. It dictates how easily we can pump it, mix it with aggregates at the asphalt plant, and then how workable the asphalt mix will be when we're trying to lay and compact it on the road. If the viscosity is too high, it's like trying to mix and spread cold, thick molasses. If it's too low, it's like trying to work with water. It won't coat the aggregates properly. To measure this, we use a device called a viscometer. There are several types, but a common one for bitumen is the capillary tube viscometer. The basic idea is to measure the time it takes for a specific volume of bitumen to flow through a very narrow, calibrated tube under the force of gravity. We do this at high temperatures, like 135 degrees Celsius or 165 degrees Celsius, because these are the temperatures used during the production and paving of asphalt. The bitumen is heated to the test temperature, poured into the viscometer, and then we simply use a stopwatch to time its journey between two marked points on the capillary tube. The time it takes, in seconds, is then multiplied by a calibration factor specific to that viscometer to get the viscosity in a unit called centistokes, or Pascal seconds. A longer flow time means a higher viscosity. This test gives us a precise, scientific value for the bitumen's flow characteristics at the exact temperatures we care about for construction. It's a much more scientific approach than just relying on the penetration test, and it's becoming the standard in modern pavement engineering, leading to what's called performance grading systems. The importance of this is massive during the construction phase. At the asphalt plant, the bitumen needs to be fluid enough, low enough viscosity, to be pumped through pipes and sprayed evenly to coat all the hot aggregates. If it's too thick, the mixing is incomplete, leading to a weak and non-uniform asphalt mix. Then, on the road, the hot mix asphalt needs to remain workable long enough for the paving machines to spread it evenly and for the rollers to compact it to the required density before it cools down and stiffens. The viscosity determines this window of workability. Ultimately, the viscosity test helps us fine-tune the entire construction process. It ensures we can achieve a uniform coating of binder on the aggregate, which is critical for durability, and that we can achieve the target density during compaction, which is critical for strength and preventing water from getting in. Improper viscosity can lead to a host of problems like poor compaction, segregation of the mix, and a weak final pavement. So, this test is all about ensuring the road is built right from the very beginning. This next test might sound a bit academic, but it is one of the most important pieces of the puzzle when it comes to the numbers side of road building. We're talking about the specific gravity test. In simple terms, specific gravity is a measure of density. It tells us how heavy a certain volume of bitumen is compared to the same volume of water. It's a ratio with no units. A specific gravity of 1.0 means it's the same density as water. Most bitumen has a specific gravity slightly greater than 1.0, usually around 1.01 to 1.05, meaning it's just a little bit denser than water. So how do we measure this? The most common method uses a small glass flask with a precise volume called a pycnometer or specific gravity bottle. The procedure is a classic weighing by difference method. First, we weigh the empty, dry pycnometer. Second, we weigh the pycnometer filled to the brim with distilled water. Third, we empty it, dry it, and weigh it again, this time filled with our bitumen sample. Finally, we top up that pycnometer containing the bitumen with water and weigh it a fourth time. It sounds like a lot of weighing, but with these 4 values, we can calculate the exact volume the bitumen sample occupies, and from that, its specific gravity. It's a meticulous process that requires precision, because even small errors can throw off our calculations later on. The temperature must be carefully controlled, as the density of both water and bitumen changes with temperature. This is why it's a standard lab procedure, done under controlled conditions. The final calculation gives us that one crucial number, the specific gravity of our bitumen. It's a fundamental physical property, like a fingerprint for that specific batch of binder. Why on earth do we need to know this? Well, bitumen is sold by weight in tons, but it's used in the asphalt mix by volume. The specific gravity is the conversion factor that allows us to switch between mass and volume. This is absolutely critical for what we call mix design. Mix design is like a recipe for asphalt. It specifies the exact proportions of aggregate, stones of different sizes, filler, and bitumen needed to create a strong, durable, and economical pavement. All these proportions are based on volume. Without an accurate specific gravity value for the bitumen, our entire recipe would be wrong. We might add too much bitumen by volume, leading to a rich, unstable mix that ruts easily. Or we might add too little, resulting in a dry, brittle mix that unravels and lets water in. It also plays a huge role in calculating the voids in the compacted asphalt mix, the small air pockets that are essential for pavement performance. In short, the specific gravity test is the cornerstone of all our quantitative calculations in asphalt technology. It ensures our recipe is accurate and the road we build has the exact composition it was designed to have. Okay, team, let's talk about something incredibly important but often overlooked: safety. We are dealing with bitumen, which we have to heat up to very high temperatures, often over 160 degrees Celsius, that's over 320 degrees Fahrenheit, to make it liquid enough to work with. At these temperatures, bitumen starts to release flammable vapors. If these vapors mix with air and find an ignition source, a spark, an open flame, you could have a sudden flash fire or even a sustained fire. This is obviously extremely dangerous for workers at the asphalt plant and on the construction site. This is why the flash and fire point test is non-negotiable. The purpose of this test is to determine 2 critical temperatures. The flash point is the lowest temperature at which the bitumen vapors will ignite for a brief moment. A flash, when a small flame is passed over the surface, but it won't keep burning. The fire point is the slightly higher temperature at which the vapors will catch fire and continue to burn for at least 5 seconds. We need to know these temperatures to define a safe maximum heating temperature for the bitumen. We must always keep the bitumen well below its flash point during storage, mixing, and application. The standard piece of equipment for this is the Cleveland Open Cup apparatus. It's a simple but effective device. We have a brass cup that we fill with our bitumen sample to a marked line. We then start heating the cup from below at a steady, controlled rate. A thermometer is suspended in the bitumen to monitor its temperature. As it heats up, every few degrees of temperature rise, we pass a small test flame across the top of the cup. We're just looking for that first, tiny, instantaneous flash of blue flame across the surface. The temperature at which that happens is the flash point. We don't stop there though. We remove the test flame, but continue heating the bitumen. We keep passing the test flame over the cup periodically. Eventually, we'll reach a temperature where the vapors not only flash, but ignite and stay burning. That's our fire point. This test gives us a clear upper safety limit. For paving grade bitumen, the flash point is usually above 230 degrees Celsius, which provides a safe margin of error above the typical application temperatures of 150 to 170 degrees Celsius. The importance here is purely about safety and risk management. A batch of bitumen with an unusually low flash point could indicate contamination with a more volatile material, like kerosene or diesel. Using such a material would be a massive safety hazard. These test results are used to create safety data sheets and handling protocols for everyone involved in the paving operation. It ensures that the foreman at the plant and the crew on the road know the absolute maximum temperature the binder can be heated to. It's a simple test that prevents catastrophic accidents, protecting lives and equipment. We've talked about what happens to bitumen when it heats up in terms of safety and softening, but there's another thing that happens. Some of it evaporates. The lighter, more volatile components of the bitumen can turn into vapor and escape into the atmosphere. This might not sound like a big deal, but it is. This process, called volatilization, leaves behind a bitumen that is harder and more brittle than what we started with. The loss on heating test is designed to measure exactly how much of the bitumen is lost through evaporation when it's heated for a prolonged period. This test is a proxy for what happens during the hot mixing process at the plant and for the long-term aging of the pavement on the road. A bitumen that loses a lot of its mass when heated will harden excessively during construction. This is called short-term aging. This premature hardening can make the asphalt mix difficult to compact properly and can make the final pavement more susceptible to cracking early in its life. We want a binder that is stable and doesn't change its properties too much when we cook it. The procedure is very straightforward. We start by taking a precise amount of bitumen, usually 50 grams, and placing it in a flat-bottomed container. We weigh it very accurately. Then, we place this sample in a specially designed oven with rotating shelves. This oven is maintained at a constant temperature of 163 degrees Celsius, or 325 degrees Fahrenheit, for 5 hours. The rotating shelf ensures that the sample is heated uniformly, and a fresh surface is continuously exposed. This 5-hour heating period simulates the high-temperature conditions the bitumen experiences during production and paving. After 5 hours, we take the sample out of the oven, let it cool down to room temperature in a desiccator, so it doesn't absorb moisture, and then we weigh it again. The difference between the initial weight and the final weight, expressed as a percentage of the original weight, is the loss on heating. For a good quality paving bitumen, this loss should be very small, typically less than 1%. A high percentage loss is a big red flag, indicating a poor quality or unstable binder. The importance of this test is all about durability and predicting long-term performance. A high loss on heating value tells an engineer that this bitumen will undergo significant hardening. This hardened binder will have a lower penetration value and lower ductility than the original material, making the pavement more brittle and prone to fatigue and thermal cracking. By specifying a maximum allowable loss on heating, we ensure that the binder we use will retain its essential flexible properties after the construction process, setting the stage for a road that can better resist the stresses that lead to cracking and failure over its service life. But how do we know what we have is actually bitumen? Bitumen is, by definition, a material that is soluble in certain organic solvents. Any part of it that doesn't dissolve is considered an impurity. These impurities could be things like salts, carbon particles, or other inert minerals. They do nothing to help the bitumen perform its job as a binder. In fact, they can be harmful. The solubility test is our chemical purity check. It tells us what percentage of our sample is active, useful bitumen, The main purpose here is to quantify the purity of the binder. A high degree of solubility is a primary indicator of the quality and refinement of the bitumen. Specifications almost always require the bitumen to be at least 99% soluble. This ensures that what you're paying for and putting in your road is almost entirely the active cementing agent that you need, and not a material bulked up with useless or detrimental filler. It's a fundamental quality control test that separates good, refined bitumen from crude or contaminated products. The test procedure is essentially a chemistry lab classic. We take a small, accurately weighed sample of bitumen, about 2 grams. We then place this sample in a flask and add a specific solvent. The most common solvent used is trichloroethylene. Although carbon disulfide was used historically, it's much more hazardous. We stir the mixture until all the bitumen appears to have dissolved, creating a dark solution. To separate out any impurities, we then filter this solution through a special filter paper or a Gooch crucible that has been pre-weighed. Any insoluble materials, the impurities, will be caught by the filter. The pure, dissolved bitumen passes right through. We then carefully wash the filter with more solvent to make sure we've gotten all the soluble bitumen off of it. After that, we dry the filter paper with the trapped impurities in an oven and weigh it. The difference in weight gives us the mass of the insoluble impurities. By comparing this to the original sample weight, we can calculate the percentage of pure, soluble bitumen. For example, if we started with 2 grams and found 0.01 grams of impurities, the solubility is 2 minus 0.01 divided by 2 times 100, which equals 99.5%. The importance of this test cannot be overstated. It's a direct measure of quality and refinement. If a bitumen sample shows low solubility, it means it's contaminated. These inert particles don't contribute to the adhesive or cohesive properties of the binder. They are just taking up space. This can lead to a weaker bond between the binder and the aggregate particles, which in turn can lead to stripping, where the binder film peels off the aggregate, and ultimately, the disintegration of the pavement. By insisting on a high solubility, say, greater than 99%, we guarantee that we are using a pure, effective binder, which is the foundation of a durable asphalt mix. Our final test might seem like an obvious one, but it's incredibly important: the water content test. Bitumen and water are enemies. When you're making hot mix asphalt, you're working at temperatures well above the boiling point of water. If there's water present in the bitumen when you pump it into the hot mixing drum, that water will instantly flash into steam. This can cause violent and dangerous foaming, where the bitumen expands rapidly in volume and can overflow from tanks and mixers. This is a huge safety risk and can also mess up the entire production process. Even small amounts of water that don't cause dramatic foaming can be a major problem. Water is the enemy of adhesion. The presence of moisture on the surface of aggregate particles prevents the bitumen from forming a strong, continuous bond. This leads to a weak point in the mix. Over time, under the stress of traffic, this can lead to a phenomenon called stripping, where the bitumen film literally peels away from the aggregate, particularly for certain types of rock. Once stripping starts, the pavement rapidly loses strength and falls apart. So, we need to make sure our bitumen is as dry as possible. The test to determine water content is a distillation process. We use an apparatus consisting of a round-bottom flask, a condenser, and a graduated receiving trap. We place a known amount of our bitumen sample into the flask along with a water-immiscible solvent, like xylene, which helps to carry over the water vapors. We then heat the flask. As the mixture boils, both the solvent and any water present in the bitumen vaporize and travel up into the condenser. The condenser, which is cooled by circulating water, turns these vapors back into liquid. Here's the clever part. Because water and the solvent don't mix and have different densities, they collect in the graduated trap in 2 distinct layers. Water, being denser than xylene, settles at the bottom of the trap. The trap is calibrated so we can directly read the volume of water that has been collected. measured in milliliters. Since 1 milliliter of water has a mass of 1 gram, we can easily calculate the percentage of water by weight in our original bitumen sample. Most specifications require the water content to be extremely low, often less than 0.2%. This test is a critical final check before the bitumen is accepted for use. It prevents dangerous foaming incidents at the asphalt plant, which protects workers and equipment. More importantly, from a durability standpoint, it ensures that we can achieve the best possible adhesion between the binder and the aggregate. A strong water-resistant bond is the secret to preventing moisture damage, which is one of the leading causes of pavement failure, especially in wet climates. By ensuring our bitumen is dry, we are building a road that is fundamentally more resistant to the destructive power of water from day one. So there you have it. The 9 critical tests that turn road building from a guessing game into a precise science. From checking its hardness with the penetration test, to making sure it won't melt with the softening point test, or catch fire with the flash point test. Each one gives us a crucial piece of data. In summary, these tests are the engineer's toolkit. They allow us to select exactly the right type of bitumen for the job by systematically considering the local climate, the expected traffic load, crucial safety factors during construction, and the long-term durability of the pavement. This is how we build roads that can stand up to scorching summers, freezing winters, and heavy trucks for decades. Now, for all of you students out there with an exam on the horizon, here's my pro tip. When you get a question about any of these tests, structure your answer in 3 parts. First, explain the purpose of the test. What property are we trying to measure and why is it important? Second, briefly describe the procedure. What are the key steps and apparatus? And third, explain the importance of the results. How does an engineer use this number to make a decision? If you follow that structure, purpose, procedure, importance, you will absolutely ace your exam questions on this topic. Mastering these tests isn't just about getting a good grade. It's fundamental knowledge for any civil engineer. You'll use it in your university laboratory work. You'll rely on it for quality control on a construction site, and it will form the basis of your research if you go on to postgraduate studies in pavement engineering. It's the science that connects the lab to the real world. Thank you so much for watching. If this lesson helped you connect the dots, please hit that like button, subscribe for more engineering deep dives, and share this video with your coursemates. I'll see you all in the next class.